A summary of the equations of motion used in kinematics. Use S equals Vt for motion with constant velocity. This car has a constant velocity. This projectile, if we look at its horizontal motion, the horizontal velocity is a constant. If motion is in a single direction, then the displacement S can be thought of as distance, and the velocity v can be thought of as speed. Use SUVAT formulae for motion with constant acceleration. So the car has a constant acceleration of 2 meters per second squared. This projectile, if we look at its vertical motion, g is used for constant acceleration, and the same is true here. Again, if motion is in a single direction, then S can be thought of as distance, and the velocities, here the velocity vectors, can be thought of as speed. If motion is given in vector form with constant acceleration, and in vector form I mean component ij form or column vector form, we can use these equivalent SUVAT formulae, and you'll notice that all of the vectors are underlined. T is a scalar, so it's not underlined. Now one of these SUVAT formulae is missing, which is this one. Because we've got vector notation here, then taking a vector and squaring it is beyond the scope of the course, so we're not going to use this formula here. And if you want to solve a problem using this formula, then you have to use a workaround, so use one of the others or a combination of the other formulae, but you can't use this one when you're given vector forms. We use this formula to work out the position vector r of an object, where r0 is the position of the object from the origin, plus s is the displacement of the object. So r, the position vector, is always measured from the origin, and r0, the initial position of the object, is measured from the origin. For example, an object starts at position A and it moves in this direction to position B. Starting position, ending position. The difference between them is given by the displacement vector S. The initial position of the particle relative to the origin was at A, and that's given by this vector r0. And together they combine to give the position vector of the particle at any point r. So the initial position of an object from some origin will be given in a question, or you'll see that on a diagram. The displacement s, well, that depends on whether you have acceleration, in which case you can use these SUVAT formulae, and you can see s here, so we can use this formula or this to replace the s here. In cases where we have constant velocity and no acceleration, then we don't use SUVAT formulae, then we use S equals Vt, then the s here is replaced with Vt. In this example, this projectile has a position vector given by this, where 3j is the initial position, and we can see that the ball here is 3 meters above the origin, hence the 3j for the initial position, and s is the displacement vector measured from this point. The acceleration is based on gravity and it's a constant, so we can use the vector form of the SUVAT formulae. The boat is given its initial velocity in vector form. The acceleration is given in vector form. Its position vector relative to some origin is equal to the initial position here, plus a displacement from that initial position. So you have these for your basic SUVAT formulae, and SUVAT again in vector form, and then for the position vector formula you have these. For projectile motion formulae, if you're given any of these in a question, then your solution should involve these formulae, but they are difficult to memorize. But make sure you know how to derive these from first principles. For example, when you start with the Suvat formulae. For most problems involving projectiles, you're better off avoiding these, and you should use the basic Suvat formulae which are given in the formula book. So stick to these methods for most solutions.